Right now, something extraordinary sits on the surface of our Sunday A region of magnetic chaos. So vast, you could fit 10 Earths inside it and still have room to spare. It appeared recently, rotating into view from the far side of our star. And the moment astronomers detected it, instruments around the world locked onto this single dark blemish. What happens next could ripple through every corner of modern civilization. They call it Active Region 4294 through 4296, a designation so complex officials had to split it into 3 separate numbered groups just to categorize its size. Amateur astronomers report seeing it with the naked eye, using nothing but proper solar filters. 5 Earths tall, 5 Earths wide, and it's rotating toward a direct line with our planet. The question hanging in the air is simple yet profound. What if this region unleashes its energy while Earth sits squarely in its path? Our sun is not a stable, peaceful sphere of light. It's a thermonuclear furnace, held together by its own gravity, a churning sea of plasma where temperatures exceed 15 million degrees at the core, and magnetic field lines twist, tangle, and snap with incomprehensible violence. Sunspots are the visible evidence of this internal war. They appear as dark regions on the solar surface, not because they're cold, but because they're cooler than their surroundings, typically around 3,500 degrees Celsius, compared to the 5,500 degrees of the normal photosphere. That temperature difference makes them appear black against the blazing backdrop. Yet a sunspot remains hot enough to vaporize anything humanity has ever built. The sunspot that emerged on December 1st is not ordinary by any measure. Patricia Leon, an amateur astronomer observing from Santiago, Chile, described it as enormously huge and complex, requiring more than 2 days just to rotate entirely past the eastern limb of the Sunday. Think about that. The sun rotates, and this single feature took 48 hours to fully come into view. Leon noted something else concerning: the delta magnetic component. In solar physics, a delta configuration means opposite magnetic polarities are packed together in the same penumbral structure. Umbrae of opposite polarity, sharing the same shadow. This is the magnetic equivalent of 2 tectonic plates grinding against each other. Pressure builds, tension accumulates, and eventually, something must give. The classification system for sunspots reveals exactly how worried we should be. Alpha regions have a single dominant polarity, simple and stable. Beta regions show a bipolar structure with distinct positive and negative areas, more dynamic but still manageable. Beta-gamma configurations indicate that positive and negative polarities are so intermixed that no clear line can be drawn between them. And then there's beta-gamma-delta, the most complex and dangerous classification, where those intertwined polarities exist within a single penumbral structure. AR 4294 has been classified as beta-gamma-delta. Magnetically speaking, it's a coiled spring, waiting to release. What makes this particular moment significant is context. We're deep within solar cycle 25, and it's been a wild journey. When this cycle began in December 2019, official prediction panels expected a weak and quiet maximum, similar to the underwhelming cycle 24 before it. They projected a peak of around 115 sunspots sometime in July 2025. They were wrong. By 2022, activity was already outpacing predictions. By 2023, NOAA revised their forecast upward, admitting solar maximum would arrive earlier and stronger than anticipated. By October 2024, scientists confirmed that solar maximum was already underway, potentially having started as early as 2 years before anyone officially acknowledged it. Sunspot counts in August 2024 reached the highest level since September 2001. This wasn't supposed to happen. The sun has been producing X-class flares with increasing frequency. On November 11th, active region 4274 produced an X5-16, the strongest flare of 2025 and the 6th largest of the entire solar cycle. It released a coronal mass ejection traveling at 1,950 kilometers per second, so fast that NOAA issued a rare G4 geomagnetic storm watch. Just 2 weeks later, another region produced multiple X-class events in rapid succession. Each one reminded us that our star operates at an intensity level that defies every major space weather institution's predictions. When AR 4294 became visible, another newcomer designated AR 4299 fired off an X1. 9 flare at 0227 Universal Coordinated Time. The eruption was captured by NASA's Solar Dynamics Observatory, a towering structure of plasma and energy breaking over the limb of the Sunday. The radiation reached Earth in 8 minutes, ionizing the upper atmosphere and triggering an R3 radio blackout across Australia. Aviation communications went dark. Maritime signals dropped out for approximately 30 minutes. An entire continent lost high-frequency radio capability because of an event that originated 93 million miles away. That flare didn't come from the giant sunspot. It came from a smaller region nearby, almost as if the sun was sending a warning shot, a preview of what the main event might deliver. Coronagraph imagery from the Solar and Heliospheric Observatory revealed a rapid partial halo coronal mass ejection associated with the blast. Billions of tons of magnetized plasma hurled into space at tremendous velocity. This particular ejection wasn't aimed at Earth. It blasted off the northeastern limb and sailed harmlessly into the void. But the geometry is changing. Every hour the sun rotates slightly, and every hour AR 4294 turns a little more toward our planet. NOAA's Space Weather Prediction Center forecasts a 70% chance of M-class flares and continuing possibility of additional X-class events. They anticipate active to G1 minor storm conditions as a coronal hole high-speed stream sweeps past Earth. By December 4th, if timing aligns poorly, we could see G1 to G2 conditions, possibly reaching KP7 at peak. Auroras might dance as far south as Toronto, Chicago, Boston, and Melbourne. Beautiful? Certainly. But beauty often masks danger. What concerns scientists isn't the immediate forecast, but the potential. AR 4294 is not simply large, it's magnetically primed. The delta configuration means energy is being stored in twisted magnetic loops that could release at any moment. When those loops reconnect, when the magnetic tension exceeds the threshold the plasma can contain, the result is a solar flare, an explosion that can release energy equivalent to billions of nuclear weapons detonating simultaneously. The largest flares can ionize Earth's atmosphere and disrupt communications within minutes of occurrence. But flares themselves are only part of the story. The real threat comes from what often follows. Coronal mass ejections are the heavy artillery of solar weather. Unlike the electromagnetic radiation of a flare, which travels at light speed and arrives in 8 minutes, a CME is a physical mass of charged particles and magnetic field, billions of tons of solar material flung outward at speeds ranging from 250 kilometers per second to over 3,000. Depending on velocity, a CME can reach Earth in as little as 15 hours or take several days. When it arrives, it collides with our magnetosphere, the invisible magnetic shield that has protected life on this planet for billions of years. Under normal conditions, the magnetosphere deflects most incoming particles, channeling them toward the poles where they create the shimmering curtains of the aurora. But when a CME is powerful enough, when its magnetic field orientation is unfavorable, it can compress the magnetosphere, distort it, and in extreme cases, temporarily punch through. That's when things become dangerous. That's when the modern world discovers just how dependent it has become on systems never designed to withstand the fury of our own star. Power grids, satellites, GPS networks, internet infrastructure, all of it connected, all of it vulnerable, and most of it running on the assumption that space weather is someone else's problem. The rules have changed. The stakes have multiplied, and the sun doesn't care. The Australian warning. When the sun spoke to Australia at 0227 Universal Coordinated Time on December 1st, 2025, it released a burst of electromagnetic radiation so intense that it crossed 93 million miles of empty space in approximately 8 minutes and 20 seconds. By the time the first photons reached Earth, the event was already over on the solar surface. But for people on the sunlit side of our planet, the consequences were just beginning. Australia bore the brunt. Across the continent, high-frequency radio communications simply stopped working. Aviation signals dropped into static. Maritime operators found themselves suddenly isolated, their equipment functioning perfectly, yet receiving nothing but noise. For approximately 30 minutes, one of the most technologically advanced nations on Earth experienced a communications blackout triggered by an explosion on a star. This was an R3 event on the NOAA radio blackout scale, classified as strong. The scale runs from R1 minor through R5 extreme. An R3 blackout means wide area degradation of high-frequency radio communication and loss of radio contact for about an hour on the sunlit side of Earth. Navigation signals experience errors. It's not catastrophic. It's not civilization ending, but it's a reminder. a tap on the shoulder from the cosmos that the infrastructure we take for granted operates at the pleasure of forces far beyond our control. The flare itself was classified as X1.9. To understand what that means, you need to understand how solar flares are measured. The classification system uses letters A, B, C, M, and X, with each letter representing a 10-fold increase in energy output. A-class flares are barely detectable above the background radiation of the sunday. B-class flares are slightly stronger, but still negligible in terms of Earth effects. Class flares are common and can cause minor radio interference at high latitudes. M-class flares are moderate, capable of causing brief radio blackouts in polar regions and occasionally at lower latitudes. And then there's X-class, the most powerful category, where numbers after the letter indicate magnitude within that extreme tier. An X1 flare is 10 times more powerful than an M1. An X10 is 10 times more powerful than an X1. The scale technically has no upper limit, though the strongest flare ever recorded was estimated around X45, a monster that erupted in November 2003 and saturated the sensors designed to measure it. An X1.9 sits comfortably in the lower range of the extreme category, powerful enough to cause significant radio disruption, strong enough to ionize the upper atmosphere and alter the propagation of radio waves, but not powerful enough to threaten satellites or induce dangerous currents in power lines. Not yet. The concerning part wasn't the flare itself, but what it represented: a new active region, still emerging over the solar limb, still partially hidden from Earth view, had already demonstrated it was capable of X-class eruptions, and behind it, rotating into ever more direct alignment with our planet, sat the largest sunspot complex in 10 years. December's ticking window. There's a window, a specific period of days when danger reaches its peak, when the geometry of Sun and Earth aligns in the worst possible configuration. For AR 4294, that window opens around December 4th and doesn't close until approximately December 7th. During those days, the massive sunspot complex will transit the central meridian of the solar disk, the region where any eruption, any coronal mass ejection, any violent release of magnetic energy will be aimed directly at our planet. Before and after that window, risk diminishes. Flares still occur, ejections still happen, but they miss us, sailing off into the cosmic void at angles that spare Earth from the full brunt of their fury. During the window, there's no margin for error. Whatever the sun releases will be coming straight for us. Victor Rogas, observing from Sedona, Arizona, captured the region while it was still emerging over the southeastern limb and noted that it appeared potentially dangerous. Valerie Lear in France described the complex magnetic structure with bright plages and absorbing filaments that follow the magnetic field lines. These are not sensational claims. These are observations from experienced solar observers who recognize when something unusual is happening. The delta configuration remains the critical factor. In solar magnetism, the arrangement of polarities determines stability. Imagine two bar magnets placed near each other. If their opposite poles face each other, north to south, they attract and settle into a stable configuration. If their same poles face each other, north to north or south to south, they repel and create tension. Now imagine those magnets embedded in a churning sea of plasma, their field lines twisted and tangled by convective motions deep beneath the visible surface. The energy stored in those twisted fields is immense, and it will eventually be released. The question is whether the release will be gradual through a series of small flares and slow reconnection events, or sudden through a catastrophic eruption that dumps all that stored energy into space at once. Delta sunspots favor the sudden option. Statistics are clear. Regions with delta magnetic configurations produce more than 80% of all major flares. They're the troublemakers of the solar surface, the active regions most likely to generate the X-class events that disrupt our technology and occasionally threaten our infrastructure. Consider what we know about the current state of solar cycle 25. This was supposed to be a quiet cycle, a continuation of the trend toward weaker activity that characterized cycle 24. The official predictions in 2019 called for a maximum of around 115 sunspots reached sometime in July 2025. Instead, activity has consistently exceeded forecasts. The cycle ramped up faster than expected. Sunspot counts reached levels not seen since the early 2000s. In October 2024, the Solar Cycle Prediction Panel finally acknowledged what had become obvious to observers. Solar maximum had arrived, possibly as much as 2 years earlier than initially predicted. and it was proving stronger than conservative estimates had suggested. This matters because solar maximum is when the most dangerous events occur. Not exclusively, of course. Large flares can happen at any point in the cycle, but probability peaks during maximum when the sun's magnetic field is most complex and active regions are most numerous. We're currently in that peak. The sun is at its most volatile, its most unpredictable, its most capable of producing the kind of event that could genuinely disrupt modern civilization. If you're enjoying this deep dive into cosmic forces that shape our world, take a moment to subscribe to Broken Zach. We explore the science and mysteries that matter, and your support helps us continue bringing these stories to light. The Carrington warning we forgot. On the morning of September 1st, 1859, a 33-year-old English astronomer named Richard Carrington was doing what he did most clear days, projecting an image of the sun onto a white screen and carefully sketching the sunspots he observed. His observatory in Red Hill, Surrey, was modest but effective, equipped with a 4.5-inch telescope that allowed him to track solar features with considerable precision. That morning, he noticed a large group of sunspots in the northern hemisphere, complex and active, the kind of feature that demanded careful documentation. Then something happened that had never been recorded before. At 11:18 local time, two brilliant patches of white light appeared within the sunspot group, intensely bright against the already luminous solar surface. Carrington watched in astonishment as the lights moved across the face of the sunspot, traveling roughly 35,000 miles in 5 minutes before fading from view. He had witnessed a solar flare, the first ever observed by human eyes, though he didn't know what to call it or what it meant. What followed the flare was unprecedented in human experience. Approximately 17.5 hours later, a massive geomagnetic storm struck Earth. This was extraordinarily fast. Coronal mass ejections typically take 2 to 4 days to traverse the distance between Sun and Earth. The Carrington CME arrived in under 18 hours, suggesting either extreme velocity or that a prior ejection had cleared the path of solar wind, reducing the drag that normally slows such events. The impact was immediate and global. Telegraph systems across Europe and North America went haywire. Operators reported receiving severe electrical shocks from their equipment. Telegraph paper spontaneously caught fire in multiple offices. In some cases, induced currents were so strong that operators could disconnect their batteries entirely and continue sending and receiving messages powered solely by geomagnetically induced electricity flowing through the wires. The aurora borealis, normally confined to high latitudes, was visible as far south as the Caribbean, Colombia, and Hawaii. In the Rocky Mountains, gold miners woke at 1 in the morning thinking dawn had arrived. So bright was the auroral light. People across the world watched in wonder and fear as the sky burned red and green in colors they'd never seen before. The Carrington event, as it came to be known, was the largest geomagnetic storm in recorded history. Estimates of its intensity suggest it was roughly double the strength of the next most powerful measured event. The DS index, a measure of geomagnetic disturbance, is estimated to have reached between -800 and -1750 nanotesla. For comparison, the March 1989 storm that collapsed the Quebec power grid reached approximately -589 nanotesla. The Carrington event was 2 to 3 times stronger than the storm that blacked out an entire Canadian province. But in 1859, there was little to damage. The world ran on muscle power, steam power, and flame. The telegraph was the height of electrical technology, and even it was a novelty most people had never used. There were no power grids to collapse, no satellites to disable, no GPS systems to scramble, no internet to go dark. The Carrington event was primarily a spectacle, a source of wonder, and some damaged equipment, but not a civilization-threatening catastrophe. We've spent the intervening 166 years building exactly those vulnerabilities. The modern world runs on electricity in ways that would have been unimaginable to Carrington and his contemporaries. The power grid isn't merely convenient, it's essential to every other system that sustains our civilization. Without electricity, water treatment plants stop operating. Pumping stations that move clean water to homes and businesses fall silent. Sewage systems that depend on powered lifts begin to back up. Hospitals lose the ability to run ventilators, dialysis machines, and refrigeration for medications. Gas stations can't pump fuel. Grocery stores can't refrigerate food or process transactions. Traffic signals go dark. Communication networks collapse as cell towers exhaust their backup batteries. Within hours of a major grid failure, the cascade of secondary effects begins to accumulate. Within days, it becomes a crisis. Within weeks, it threatens lives on massive scale. A Carrington-class event today wouldn't merely be inconvenient. Multiple studies have attempted to estimate the damage. Lloyd's of London commissioned a report examining the potential cost of a Carrington-level storm striking the United States. Their estimate ranged from $600 billion to $2.6 trillion, depending on severity and duration of impacts. More importantly, estimates focused primarily on direct damage and immediate economic disruption. They didn't fully account for cascading failures that would result from extended power outages across multiple states or regions. The vulnerability lies primarily in high-voltage transformers that form the backbone of the power grid. These massive devices, some weighing over 400 tons, step voltage up for efficient long-distance transmission and step it down for local distribution. They're expensive, custom-built, and require 12 to 18 months to manufacture under normal conditions. The United States has approximately 2,000 of these extra high-voltage transformers, and there's no significant domestic manufacturing capacity. Most are built overseas. There's no strategic reserve of spare transformers waiting to replace damaged units. A geomagnetic storm that destroyed or severely damaged even a fraction of these transformers could result in power outages lasting not days, but months or potentially years. The mechanism of damage is subtle but relentless. When a CME strikes Earth's magnetosphere, it induces electric currents in long conductors at the surface. Power lines act as antennas, gathering these geomagnetically induced currents and channeling them into the grid. The currents flow through transformers seeking ground, but transformers are designed for alternating current at 50 or 60 hertz, not the quasi-direct current produced by geomagnetic disturbances. The induced currents cause transformer cores to saturate magnetically, generating heat in places the equipment was never designed to handle. Insulation degrades. Hotspots develop. In extreme cases, windings can melt, oil can catch fire, and the transformer can be destroyed. This isn't theoretical. It happened in March 1989 inches, Quebec. A geomagnetic storm, approximately one-third the intensity of the Carrington event, caused the Hydro-Quebec grid to collapse in 92 seconds. 6 million people lost power for up to 9 hours in the middle of harsh Canadian winter, but damage extended further. A transformer at the Salem nuclear plant in New Jersey was destroyed by induced currents. Within 2 years of the storm, 11 nuclear plants reported failures of generator step-up transformers likely linked to the event. The storm was moderate by historical standards. It wasn't even close to Carrington class, and yet it demonstrated exactly how vulnerable our infrastructure is to space weather. Richard Carrington suspected a connection between the solar flare he observed and the geomagnetic storm that followed, but he was cautious. Famously writing that one swallow doesn't make a summer, he couldn't be certain that correlation implied causation. Today, we understand the physics completely. Solar flares release electromagnetic radiation that arrives at light speed, causing immediate ionospheric disturbances. Coronal mass ejections follow, carrying magnetized plasma that interacts with Earth's magnetic field to produce geomagnetic storms. The connection isn't speculative, it's measured, modeled, and monitored continuously by satellites and ground-based instruments. What we haven't done is act on that knowledge at a scale commensurate with the risk. The power grid remains largely unprotected. Spare transformer capacity remains inadequate. Warning systems can provide hours to days of notice for an incoming CME, but preparations that can be made in that time frame are limited. Operators can reduce load. They can open certain circuits to prevent induced currents from flowing through critical equipment, but they can't harden a grid in hours that should have been hardened over decades. The Carrington event was a warning written in auroral fire across the sky of 1859. We marveled at it, we documented it, and then we built a civilization that forgot the lesson it should have taught us. Whispers in the tree rings. In 2012, a physics graduate student at Nagoya University in Japan made a discovery that would rewrite our understanding of solar violence. Miyake wasn't looking for anything extraordinary. Her project involved a new, highly sensitive technique for measuring carbon-14 inches tree rings, a refinement of radiocarbon dating that allowed analysis of individual annual growth layers, rather than average samples spanning decades. She traveled to Yakushima Island in southern Japan, famous for its ancient cedar trees, some nearly 1900 years old. She cut a slice from an old stump, counted back through the rings, and began measuring radioactive carbon content year by year. What she found in the ring corresponding to 774 to 775 AD was impossible to ignore. The carbon-14 level spiked by approximately 12% compared to adjacent years. This wasn't a gradual increase or measurement error. It was a sharp, single-year jump, roughly 20 times greater than normal year-to-year variation, caused by ordinary cosmic radiation. Something had happened in 774 or 775 that dramatically increased the production of carbon 14 inches Earth's atmosphere. Something powerful, something brief, something that left its signature in the wood of trees around the world. Carbon-14 forms when high-energy particles from space collide with nitrogen atoms in the upper atmosphere, knocking out protons and converting nitrogen into a radioactive isotope of carbon. This carbon-14 then combines with oxygen to form carbon dioxide, which circulates through the atmosphere and gets absorbed by living things. When a tree grows a new ring, it incorporates the carbon dioxide available that year, including whatever carbon-14 is present. When the tree stops growing, when that ring is complete, the carbon-14 is locked in, slowly decaying over thousands of years at a known rate. But Miyake wasn't trying to date the tree. She was trying to measure cosmic ray intensity over time, and the spike in 774 told her that cosmic ray flux had temporarily increased by an enormous amount. Other researchers quickly confirmed her finding. The same spike appeared in tree rings from Germany, Russia, the United States, Finland, and New Zealand. Whatever had caused the event, it was global. A matching surge in beryllium-10, another cosmogenic isotope, was found in Antarctic ice cores, corresponding to the same period. The evidence was unambiguous. Earth had been bombarded by an intense burst of high-energy particles sometime around 774 or 775 AD, and the signature of that bombardment was preserved in trees and ice around the planet. The leading explanation was a solar storm. The sun produces energetic particles during flares and coronal mass ejections, particles that can reach Earth and interact with the atmosphere in exactly the way needed to produce carbon-14 and beryllium-10. But the scale was troubling. The Carrington event, the largest solar storm in recorded history, didn't produce a detectable spike in the cosmogenic isotope record. It was too small. Whatever happened in 774 was at least 10 times more powerful than the Carrington event, possibly much more. Some estimates suggested it was 80 times stronger. These events are now called Miyake events, named after the graduate student who first identified them. Since her initial discovery, researchers have found additional spikes in the tree ring record. Another occurred in 993 to 994 AD, about 60% as strong as the 774 event. Others have been identified around 660 BC, 5,259 BC, 5,410 BC, and 7,176 BC. The most powerful event yet discovered occurred approximately 14,300 years ago, preserved in ancient trees recovered from eroded riverbanks in the French Alps. That event was roughly twice as strong as the 774 spike, which itself was already an order of magnitude beyond anything in the historical record. The implications are staggering. These events aren't hypothetical, they happened. The evidence is written in ancient wood and ancient ice, archives that have no reason to lie and no capacity for exaggeration. The sun has produced storms of extraordinary power multiple times during the Holocene, the geological epoch encompassing all of human civilization. These storms didn't end the world. Life continued. Civilizations rose and fell for reasons unrelated to solar activity. But these storms occurred before we built a technological infrastructure that depends on the very systems most vulnerable to solar bombardment. Imagine a Miyake event occurring today. Not a Carrington event, not the storm we usually cite as worst-case scenario, but something 80 times more powerful. The Carrington event would collapse power grids and damage transformers. A Miyake event would do something far worse. The radiation dose at aircraft altitudes would be dangerous, possibly lethal for passengers on polar flights. Satellites would be bombarded with particles that could fry their electronics instantly, not through slow accumulation of charge, but through direct damage to circuits and components. The ionospheric disturbance would be so severe that GPS might be unusable for days, not hours. Power grids would face induced currents beyond anything they were designed to withstand. Cascading failures would be faster, deeper and more difficult to recover from than any scenario currently modeled by emergency planners. The historical record offers a few tantalizing hints about what people experienced during these events. The Anglo-Saxon Chronicle contains an entry for 774 that describes a red crucifix seen in the sky after sunset. This is consistent with a powerful aurora visible at unusually low latitudes. Chinese records from the same period mention abnormal celestial phenomena, but documentation is sparse. These societies had no framework for understanding what they were witnessing. What we can say with confidence is that Miyake events are real, that they occur with some regularity over millennial timescales, and that they represent a category of solar violence far beyond anything in the historical record. The rough frequency appears to be approximately 1 event per 1,000 years. Though statistics are uncertain, given the limited number of confirmed examples. 1,000 years is a long time by human standards, but a blink in geological terms. The last confirmed Miyake event occurred in 993 or 994 AD, slightly over 1,000 years ago. We're statistically within the window where another could occur. There's debate among scientists about whether these events are even produced by the Sunday. The energy required is extreme, beyond what standard models of solar flares can easily explain. Some researchers have proposed alternative explanations, including supernovae or gamma-ray bursts from distant sources. But evidence tilts toward a solar origin. The isotope ratios match what would be expected from solar energetic particles. The events appear to have durations measured in years, rather than brief pulses expected from extrasolar sources. And the sun is demonstrably capable of extreme behavior. We simply may not have observed the full range of what it can do. This uncertainty is itself unsettling. We don't fully understand the mechanism that produces Miyake events. We can't predict when the next one will occur. We've only recently recognized that such events exist at all, thanks to Fusa Miyake's careful work with tree rings just over a decade ago. Our ignorance is profound, and yet we've built a civilization that would be devastated by such an event, a civilization whose survival in its current form may depend on the sun continuing to behave within bounds we've only recently discovered it can exceed. When systems fail, let's imagine it happens, not hypothetically, not as an abstract possibility to be considered and dismissed, but concretely, specifically, with all the mundane details that would define the experience for ordinary people. A massive coronal mass ejection erupts from a sunspot complex aimed directly at Earth. Forecasters detect it immediately. Coronagraph images show a full halo expanding outward from the sun, indicating the material is headed straight for us. Velocity measurements confirm the worst. This is a fast CME, traveling at over 2,000 kilometers per second. Impact is expected in less than 18 hours. Warning messages go out to power grid operators, satellite companies, airlines, and government agencies. The public is told to prepare for potential disruptions. Most people hear the news, shrug, and continue with their days. Geomagnetic storms happen, nothing to worry about. The CME arrives ahead of schedule, slamming into Earth's magnetosphere in the early morning hours. The magnetic field orientation is the worst possible. Southward, pointing, which allows solar material to couple efficiently with Earth's magnetic field. The magnetosphere compresses violently. Geomagnetically induced currents begin flowing through long conductors at the surface. Power lines, pipelines, communication cables. Within minutes, the first transformers begin to overheat. Grid operators, many of whom were already implementing protective measures, watch their systems destabilize faster than they can respond. Circuit breakers trip. Load balancing fails in several regions simultaneously. Voltage collapse cascades through interconnected networks. The lights go out. The first hour is confusion. In densely populated areas, the outage seems like any other blackout, annoying but temporary. People reach for their phones to check social media, to find out what happened, to see how long before power returns. Cell service is spotty. Towers have backup batteries, but the network is congested with everyone trying to connect at once. News websites load slowly or not at all. Those who manage to get information learn that this isn't a local outage. It's regional. It may be national. The scope is still unclear. By the second hour, traffic has become chaotic. Every intersection without power is a four-way stop, but many drivers don't treat them that way. Accidents snarl major routes. Emergency services are responding to multiple incidents simultaneously. Their communications hampered by overloaded and partially degraded networks. Hospitals have switched to backup generators, but some are discovering that the geomagnetic storm has damaged sensitive equipment. Diagnostic machines give erratic readings. Monitoring systems glitch. Staff improvise, falling back on older methods. Paper charts, manual measurements. By the 4th hour, the sun has risen on a changed landscape. In unaffected regions, life continues more or less normally, but those areas are fewer than expected. The geographic footprint of damage is becoming clear. Multiple states have lost power entirely. Others have partial service, with utilities scrambling to isolate damaged sections and restore what they can. Stock markets don't open. Financial systems that depend on precise timing synchronization are experiencing failures. GPS satellites are still transmitting, but signals are degraded, and ground-based systems that rely on GPS for timing are misbehaving. For people in affected areas, the 4th hour brings the first real inconveniences. Refrigerators have been off long enough that food is beginning to warm. Those with gas stoves can still cook, but electric stoves and microwaves are useless. Water still flows from taps because elevated storage tanks maintain pressure through gravity, but the pumps that would refill those tanks aren't running. No one worries about water yet. The outage is only a few hours old. Surely power will return soon. By the 12th hour, the mood has shifted. This is no longer a minor disruption. Cell phone batteries are dying and there's no way to recharge them. Information becomes scarce and unreliable. Rumors spread. Some say the entire country is dark. Others say power will be restored by evening. No one knows for certain because normal channels of communication are compromised. People begin to realize how dependent they are on electricity for things they never consciously thought about. The first night is long. Cities that normally glow with light are dark, revealing stars that urban residents have never seen. The novelty wears off quickly. Without heating in cold climates or cooling in hot ones, homes become uncomfortable. People layer clothing or open windows, making do with what they have. Most assume this will be over tomorrow. Major infrastructure failures don't happen in modern countries. This is temporary. By the 24th hour, water pressure begins to drop in some areas. Elevated tanks are depleting and pumps remain offline. People who turn on their taps find only a trickle, then nothing. This is when anxiety starts to build. Water isn't optional. You can go days without electricity. Uncomfortable but survivable. You can't go long without water. Grocery stores, the few that open with cash-only transactions and manual record-keeping, begin to see runs on bottled water. Supplies that seemed adequate for normal demand disappear within hours. The 36th hour brings the first real shortages. Gas stations can't pump fuel without electricity. Even those with generators are running low on diesel. Trucks that would normally resupply stores are stuck, unable to refuel, unable to navigate efficiently without GPS, facing roads clogged with vehicles that have run out of gas. The supply chain, that invisible network that keeps modern society fed and functioning, begins to stutter. Perishable food in warehouses is spoiling. Refrigerated trucks are becoming expensive metal boxes. By the 48th hour, the contours of the crisis are clear. This isn't a brief outage that will be resolved with a few repairs. Transformers have been destroyed, not tripped offline, but physically damaged. Their windings burned, their oil contaminated, their cores saturated beyond recovery. Replacing them will take months under the best circumstances. Some can't be replaced at all without manufacturing new units, a process that requires 18 to 24 months in normal times and longer when demand suddenly spikes. Utilities are performing triage, trying to restore power to the most critical facilities first. Hospitals, water treatment plants, emergency services. But there isn't enough generating capacity that survived the storm, and the transmission lines needed to deliver power are themselves damaged in places. 48 hours without electricity is survivable for most people. It's uncomfortable, inconvenient, and frightening, but it's not fatal. The danger lies in what happens next. If power is restored within a week, society can recover. People will have stories to tell. Businesses will count their losses and life will resume. If power remains out for weeks or months, the calculation changes entirely. Food runs out, water becomes critical. Medical conditions that depend on electricity for management become life-threatening. The social fabric, already strained, begins to fray. This scenario isn't fantasy. It's the explicit warning contained in multiple government and industry studies. The Federal Energy Regulatory Commission has identified 30 critical high-voltage transformers whose loss could cause cascading failure across the grid. Some analyses suggest that simultaneous loss of as few as 9 key transformers in the wrong combination could result in a coast-to-coast blackout. Recovery time for such an event wouldn't be measured in days. It would be measured in months or years, depending on availability of replacement equipment and the extent of secondary damage caused by the outage itself. The path forward. Water infrastructure is considered critical in emergency planning. Utilities prioritize water treatment plants when allocating emergency power. The loss of the grid isn't merely an inconvenience, but an existential threat. The technology that delivers clean water to hundreds of millions of people depends entirely on continuous availability of electricity. Remove that electricity for long enough, and the consequences aren't speculative. They're biological certainties. The modern world is a machine of staggering complexity, billions of interlocking parts, moving in coordination across continents and oceans. We don't see the machine because we live inside it. The food on grocery shelves appears as if by magic. The gasoline in our tanks flows from refineries connected to pipelines, connected to tankers, connected to oil fields on the other side of the world. The medications in our cabinets were manufactured in facilities using raw materials sourced globally, distributed through networks that span nations. None of this coordination happens by accident. It happens because of electricity, because of communications, because of computers tracking inventory and routing shipments and processing payments billions of times per day. Remove the electricity and the machine stops. Not gracefully, not with orderly shutdown, but violently, catastrophically, with components failing in cascades that ripple outward from the initial disruption. The question isn't whether another Carrington event will occur. It will. The question is whether we'll be ready when it does. Right now, the answer is almost certainly no, but that doesn't have to remain the answer. The technology exists. The engineering solutions are known. The cost, estimated at $10 to $30 billion to protect the entire national grid, is a fraction of annual military spending. And yet, the money hasn't been allocated. The work hasn't been done. What you do with this knowledge is up to you. But the knowledge itself is no longer something you can claim not to have. The sun continues its ancient work. Nuclear fusion at its core, magnetic fields twisting and reconnecting at its surface, plasma streaming outward in a wind that touches every planet in our solar system. It's been doing this for 4.5 billion years. It will continue for another 5 billion. We are temporary guests in a cosmos that operates on timescales that dwarf our brief existence. And yet, for this moment in geological time, we're here. We're conscious. We're capable of understanding the forces that could harm us and potentially of protecting ourselves against them. The sunspot will rotate across the solar disk in the coming days. It may flare spectacularly. It may decay quietly. Either outcome is possible. Neither outcome changes the underlying reality that the sun has produced Carrington events before and will produce them again. If this exploration has changed how you understand our place beneath the sun, if you found value in this journey through solar science and cosmic forces, I invite you to watch another video we've created. It's a great one, diving even deeper into the mysteries that surround us. We'll see you in the next video.